Hello. So we are continuing to talk about our logarithms, expanding and condensing. Now we're going to focus on. So we learned how to rewrite those logarithmic expressions into exponential expressions and vice versa. Now we're going to talk about how to condense them and how to expand them, and that's going to come with some properties, like I mentioned in the previous video for 5a. Remember, logarithms are inverses of exponents, of exponential functions. So just like our exponential properties and rules, logarithms are going to have their own properties and rules. So remember, when we have exponents with the same base and we multiply them, so let's say we have something like x squared times x cubed, what do we do with those exponents? We add them, so we get x to the fifth. If we're doing something like division, maybe I have x to the fifth divided by just x to the first power. What do I do with my exponents? I subtract them. So that would give me x to the fourth power. So because these are our exponential properties, logarithmic properties are going to be the opposite of that because they're inverses of each other. So I'm listing three very important properties of exponents. We have the product property, the quotient property, and the power property. So if I have two logs with the same base and they're being added together, then I can multiply those two arguments together. So if I have, let's look at example 1 part A. I have log of A plus log of N. The bases for both of those logs are 10. Remember, that's the common base. And so the arguments are different. And so because I'm adding them, what do I do with my arguments? I multiply those arguments together. So this would simply become the log of AN. Looks like Logan. But it's the log, really base of 10, but you don't have to write that, of whatever A is times whatever N is. So if I'm adding two logarithmic expressions together, I'm going to multiply the arguments if the bases are the same. The quotient property is when I'm subtracting two logarithmic expressions from one another. Again, the bases need to be the same. So when I'm subtracting those logarithmic, I combine them into one by dividing the arguments. The last property we're going to talk about is the power property. So if you have a coefficient, so a number in front of your logarithmic expression, that is going to become the exponent of your argument. So I'll give you a quick example of that. Let's say we have some number, 4, log base 3 of, 2. I'm just making this up. This is our number, the log base of 3 of the argument of 2. The power property says that I can rewrite that as the log base 3 of 2 to the fourth power, which then I could just simplify of log base 3 of what's 2 to the fourth power. Well, that would be 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. Nope, that's wrong. 2 to the 16. Right? 2 squared, 2 cubed, 2. Yeah, 2 to the 4. Okay, so let's try to put these all together. Notice I'm giving you an expression that involving addition and subtraction of these logarithmic in log form. So we're going to apply the product property, the quotient property, and the power property. Typically, we read from left to right, so I'm going to work in that order, but it doesn't really matter here. So when I'm looking at part B, I see log of 9 plus 3 log of 2 minus log of 3. First thing I need to notice is, do they have all the same base? Yes, they do, because they all have a base of 10. Remember, that's that common base. So log of 9 is being added to 3 log of 2. So when I add two logarithmic expressions together, I'm going to multiply the arguments. But what I notice in that second part of the expression is I need to apply the power property. I have a coefficient of 3 in front of my log, so I'm going to raise my 2, the argument, to the third power. So really I can rewrite this as, this is going to be the log of 9 plus the log of 2 cubed minus the log of 3. We know that 2 cubed is 8, so really you could have just written the log of 9 plus the log of 8 minus the log of 3. And now I can start applying the product property and the quotient property. I'm adding first, so I'm going to multiply my two arguments together, applying that product property. So this is going to be the log of 9 times 8, still minus the log of 3. And I'm going to write really big right here, and then I'll just condense it later on. I know that 9 times 8 is going to give me 72 minus the log of 3. Well, now I'm subtracting my two logs, so I'm going to apply the quotient property. I need to make sure that I'm going in order from left to right. So the log of 72 minus the log of 3 is going to give me the log of 72 divided by 3. And then again, I can simplify that one more time into just the log of 24. So I'm taking major baby steps here. I am not expecting that you write down every single step for these problems, but just for, the first couple ones, I want to show you exactly where I'm getting this information from. And that came out really ugly. I'm sorry about that. Okay, so let's try this again. Part C, I have 1/2 log of x minus 2 log of y minus 3 log of z. So I noticed that I have a coefficient on all those terms, so I need to apply the power property. I'll probably go ahead and do that first and then go ahead and apply my quotient property because I've noticed that it's all subtraction. There's no addition there, so I'm not going to use the product property at all. So applying the power property, coefficients become the power. So this is really log to the log of x to the 1/2 power. Well, what is x to the 1/2 power? That's just the square root of x minus log of y squared minus log of z cubed. I'm using the coefficient as the power, okay? So now that I'm subtracting these three terms, I can use my quotient property. So anytime you see a subtraction between logs, you know you're going to have a division symbol, all right? So what I can do here is I can say that this is going to be the log of the square root of x divided by y squared, and it's also being subtracted with the z cubed. So z cubed will also be in my denominator. So this is technically my final answer. And I want you to think about this as just numbers, because when I first was looking at this problem, I was expecting to see something like the square root of x divided by y squared and then all of that divided by z cubed, because I'm subtracting the first two, which is a division problem, and then I'm taking that result and subtracting something else, which would have given me another division problem. But that's not the case here. Think about this as a number problem. If I had 24 divided by 2 divided by 3, if I work from left to right, 24 divided by 2, that would be 12. 12 divided by 3 is 4. This is the same exact thing as 24 divided by 2 times 3, which is 6. 24 divided by 6 is also 4. So looking at that in this perspective, 24 is being divided by 2. 24 is also being divided by 3. So I'm getting that same quotient of just 4. I can combine those last two by multiplication and keep them in the denominator as I did here. So whatever is following the subtraction sign is going to be going in your denominator. You're always going to have just one division problem if you see a subtraction sign, whether that's one subtraction signs, two subtraction signs, however many you see, it's going to create one division problem. Whatever is following a subtraction sign will end up in the denominator. You don't get a fraction within a fraction within a fraction. I would not do that to you, okay? I know we've had our fair share of that, but this will be a little bit easier, okay? And there you go. So it would just be log square root of x divided by y squared z cubed, okay? And this, in the fourth part of this example, part D, I'm looking through, I have the natural log, and remember natural log has a common base of e, so the natural log of a plus b plus the natural log of a minus b minus 2 natural log of c. So I know that I have to apply my power property to that last part because I have a coefficient of 2. So I'm going to go ahead and rewrite it just applying that power property, and then I'll go back and apply my product and my quotient property. If you're starting to get a hang of this, you can obviously put it in all at once. Some of you are going to be able to see that, oh, I'm going to do, product property here, quotient property here, power property here. That's great. You don't have to take baby steps. I'm just trying to show you in the beginning. Okay, so I'm still going to have my natural log of a plus b plus my natural log of a minus b, and then applying that power property, this is going to be subtracting the natural log of c squared. So because I have an addition first, that means I'm going to apply the product property. So I'm going to multiply the a plus b with the a minus b. Well, hopefully you recognize what that's going to give us if we FOIL it out. That's the difference of squares. The difference of squares factors into an a plus b and an a minus b. So when I multiply a plus b to a minus b, I'm actually just getting the natural log of a squared minus b squared. Still subtracting that natural log of c squared. Natural log of c squared. So now that I have a subtraction problem, I'm going to apply my quotient property. So this is going to be the natural log of a squared minus b squared divided by c squared. And you can put that in parentheses if you want to, if it's more aesthetically pleasing for you, or if it's just kind of more organized for you. You do not have to put the parentheses at all. If you just want to put the parentheses in the numerator, that's totally fine too. Whatever your personal preference is for that, it's kind of just up to you. But that is our final answer. Okay, so that's condensing. Expanding obviously is going to be going in the opposite direction. So if I give you something where you see that those two arguments are being multiplied together, like let's say you see a 5 times an x, well then that will tell you, hey, they're being multiplied together, which means I can expand them by saying, oh, well, that would just be the log of 5 plus the log of x. Or if you see a division problem, then you know you're going to be subtracting those logs. If you see an argument raised to a power, then you know that that power is the coefficient of that log. So we're working backwards here. Again, you can kind of start in whatever way that you want. Division is obviously the most identifiable, I guess I would say. So when I'm looking at part A in example 2, I know that I had to have had the natural log, the natural log of this 5x to the 7th being subtracted with the natural log of y, because that gave me the division problem. But I'm not done yet, because I know that 5 times x was using my product property, and I also see that x is being raised to the 7th power, which means I was applying the power property. So I need to separate the 5 with the x to the 7th power. So I'm going to do that by addition. So this is really the natural log of 5 plus the natural log of x to the 7th minus the natural log of y. And I'm still not done yet because I have an argument raised to a power. So that power of 7 was originally a coefficient. So now I have the natural log of 5 plus 7 natural log of x minus the natural log of y. And I have expanded that logarithmic form. Okay. So going over to part B, now I have log base 6 of 3x to the 4th power. So this one actually has a base that's not 10 and it's not e, it's not a natural log, and that's totally fine. We are not going to do anything with those bases. The only thing that we need to look out for is if we were condensing, we would want to make sure that all of the bases are the same. But because we're expanding here, then we know originally all those bases were the same because we were able to condense it into one term. So what I see going on here is I see that a 3 is being multiplied to the x to the 4th power. So 3 and x to the 4th are being multiplied. So that means I can separate them by addition. So I have the log base 6 of 3 plus the log base 6 of x to the fourth. I also notice that x is being raised to a power, so that means the power property was applied, so that 4 needs to be rewritten as a coefficient. So this is going to be log base 6 of 3 plus 4 log base 6 of x, and that is it. Part C, we have log base 3 of 5 over 12x. So I see that division problem, so I know that I need to subtract some logs. So I can immediately jump in and say log base 3 of 5 subtract log base 3 of 12x. Log base 3 of 5 is done. I cannot do anything else with that. However, I know that the 12 and the x are being multiplied together, so that means they were originally being added. So I have log base 3 of 5 minus log base 3 of 12 plus log base 3 of x. Okay, now these two things are being added together after they have been subtracted from one another. So you need to be careful about that. You do need to put those parentheses there. If you want to drop those parentheses, then you would have to write it. I'll come down here and squish it all together. You would have to put your log base 3 of 5 minus your log base 3 of 12 minus your log base 3 of x. Because think about that. If I were to give you this problem with two subtraction signs, you would have had your division problem and you would have wrote it just like it was originally in part C. So you have to be careful with that. These two are the exact same thing and they are both absolutely 100% correct. You just need to be careful because if you do not, put those parentheses there, then that would be incorrect. All right, moving on to part D. So because we have log base 5 of the square root of a fraction, everything in that fraction is being taken the square root of. So that means that whole entire fraction is being raised to the 1/2 power. You know, you can rewrite it as that. Like you can say that this is log base 5 of x minus 1 divided by x plus 1 raised to the 1/2 power. That's the exact same thing. And because it's the exact same thing, because I'm raising my argument to a power, then I can apply that power property. So I can rewrite this as 1/2 of log base 5 x minus 1 divided by x plus 1. And so now I see, oh, that's a division problem. I'm going to have a subtraction of all of this. So it'd be 1/2 of the log base 5 of x minus 1 minus the log base 5 of x plus 1. I want to make sure I put those outer parentheses there because that 1/2 applies to everything in the subtraction problem, because everything is being, in this division problem, is being raised to that 1/2 power. So again, if you want to distribute that 1/2 and write 1/2 of log base 5 of x minus 1 minus 1/2 of log base 5 x plus 1, that's totally fine as well. Remember, they're both underneath the square root, so they both have a power of 1/2. Okay, so that's expanding and condensing. You really just have to take it step by step, piece by piece, and apply those three properties: the power property, the product property, and the quotient property. Okay, and obviously it goes one way or the other way depending on if you're expanding or condensing. So now we want to use approximations to actually evaluate. So it tells me in the directions for example 3 that the log base 3 of 4 is approximately 1.262 and the log base 3 of 5 is approximately 1.465. So we're going to use those approximations to actually evaluate the log. we're still going to be applying our product property, our quotient property, our power property, because in a sense, we need to make whatever's given to us in the form of either log base 3 of 4 or a log base 3 of 5, because those are the only approximations that we know. Okay, and we're doing this without a calculator. So for the first one, I see log base 3 of 4 divided by 5. Well, I know that when I'm dividing, that's going to turn into a subtraction property, or problem, excuse me. So this is really log base 3 of 4 minus log base 3 of 5, which is perfect because I know the approximations of both of those terms. I know that the log base 3 of 4 is 1.262, and I know that the log base 3 of 5 is 1.465. And so now I'm just doing some simple math, even though it's decimals and you hate them, it's fine. You can do this. 1.262 minus 1.465 is going to give us a negative 0.203. And so that is our answer. Okay. When I see part B, I have the log base 3 of the square root of 5. Well, I'm getting kind of happy because I know the log base 3 of 5's approximation, but I don't know the square root of 5. So if we rewrite the square root of 5 as 5 raised to the 1/2 power, then we can use our power property. So that's exactly what we're going to do. This is really log base 3 of 5 to the 1/2 power. And so using our power property, this is going to turn into 1/2 of log base 3 of 5. So that's really 1/2 of the approximation 1.465. So again, simple math, but you still got to, kind of use your brain a little bit. Or if you want to cheat and put that in the calculator, I guess that's fine too. Who am I to stop you? But half of this we know is going to be 0.7325. And then here again, so notice what we have here. We have the log base 3 of 12. Okay, well, we know we're trying to get to the log base 3 of 4 or the log base 3 of 5 or one or the other. So I need to think about what two numbers were multiplied together to get me 12. Well, it could be 1 and 12, but that doesn't help me because this is not a 1 or a 12, and that's not a 1 or a 12. So that's out. I could use 2 and 6. Again, that doesn't help me because I only know log base 3 of 4 and log base 3 of 5. So I go to 3 and 4. And you may be thinking to yourself, well, Miss Treese, you don't know log base 3 of 3. But we do. So let's rewrite this as the log base 3 of 3 plus the log base 3 of 4, because that's expanding, and that would give us log base 3 of 12, correct? Absolutely, using our product rule. Log base 3 of 4, we know that approximation is the 1.262. I know what log base 3 of 3 is. It's 1. Remember, when your base and your argument are the same, that is always going to be a value of 1. If I rewrote log base 3 of 3, let's say I put equal to x there, base raised to the exponent equals the argument, 3 to the x power equals 3. What's the value of x? 1. Anytime your base and your argument are the same number, that's going to give you a value of 1. So I knew that value even though it didn't give it to me in the directions. And so now I'm just adding 1 plus 1.262. So obviously that's going to give me 2.262. Not too bad. Okay. We're going to do the same thing in example 4, but instead of me giving you an approximation of the number, I'm just going to substitute and say, well, this is x and this is y, or this is, z or a or b or whatever. Okay, so now it's saying use log base 3 of 4 is equal to x and log base 3 of 5 is equal to y. So your final answer is going to be in terms of x and y. So here we go. We have log base 3 of 20. Well, I know that I can expand that. What two numbers multiply to give me 20? 2 and 10, 1 and 20, 4 and 5. Ding, 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 ding. 4 and 5 is what I want. I can rewrite that as the log base 3 of 4 plus the log base 3 of 5. That's an equivalent form. Well, if I know that the log base 3 of 4 is x and the log base 3 of 5 is y, then my answer is x plus y. And of course, you can write that in the opposite order. Addition is commutative and associative and all that fun stuff. So you could put that as x plus y if you wrote it as log base 3 of 5 plus the log base 3 of 4, and that's totally fine. All right, and in E, we have the log base 3 of 64. So again, I'm thinking to myself, what are some factors of 64, incorporating that 4 or that 5 to get me where I need to be? Well, 5 is not a factor of 64, so I know that I'm not going to use the log base 3 of 5 in any kind of way, so there won't be a y in my answer. But I know that 4 is a factor of 64. And how can I get that? Well, I know that 4 times 4 times 4 is 64. Well, what's another way of writing that? What about 4 to the third power? So if I rewrite this as log base 3 of 4 to the third power, then I can use my power property. And I can make that exponent of 3 into a coefficient. And so now I'm here. And now I can do some substitution because I know the log base 3 of 4 is x. So this is just 3x. And even if you left it as 4 times 4 times 4, like writing it as log base 3 of 4 plus log base 3 of 4 plus log base 3 of 4, that's fine. That's the correct answer. And what would you have gotten there? You would have gotten x plus x plus x. Well, what is x plus x plus x? 3x. So it doesn't matter if you were applying that product property or the power property for this particular problem. And then we have log base 3 of 5 divided by 16. So obviously we know we have a y. That's log base 3 of 5. Log base 3 of 5 minus the log base 3 of 16. That's giving me the division problem. Well, I know that 16 is 4 times 4, or 4 squared. So again, I can rewrite that using my power property. And so now I'm going to do some substitution. This is y minus 2x. This one would need to be in that exact order. You could not put 2x minus y. Why? Because that would mean you would have a 16 divided by 5 and not 5 divided by 16, which is a completely different answer. So you need to be very careful of when you see that division problem, whatever's in your numerator needs to be before the subtraction sign, and whatever's in your denominator needs to be after the subtraction sign. And so going to the last part of our notes, two different things that we want to touch on is rewriting our logs using a different base. So when you just press log on your calculator, like the log of 8 or the log of 11 or the log of 100, there's not a base there that you can input. So that means that your calculator is assuming that you're using that common base of 10. We talked about that in the 5A notes, right? Well, what if we need to change our base? So how do we do that? And it's just as easy as this change of base formula. So if I have a log base C of A, to make it have that common base, the base of 10 or E, depending on if we're using a natural log or a log, all we're going to do is we're going to take the log of the argument and divide it by the log of the base. So what does that look like? In example 5, part A, if I have log base 3 of 8, then that means I'm going to change my base so that they have the common base of 10, then I'm going to take the log of my argument and divide it by the log of the original base. And that's it. Okay, that is it, guys. And you can leave it like that fraction. depending on what the directions say. So our directions here say to rewrite and evaluate using common logarithms. Well, I've rewritten it so that they have common bases. However, I haven't evaluated it. So here's where I can just go in my calculator and say log of 8 divided by the log of 3. And when I do that, I get the approximation of 1.893. If the directions would have just said to rewrite, then I could have left it as that log of 8 divided by log of 3. But it said evaluate as well. So I actually want to type that in the calculator and get that decimal value. Okay, for part B, this would be a good place where you could just pause and try to work it out yourself because it's super easy. Change of base. Originally, we have log base 7 of 11. So to make them have a common base, what I'm going to say is I'm going to do log of 11. Good. Over log of 7. I've rewritten it. Now I need to evaluate. Evaluating that, I will get 1.232. Not too bad, right? And lucky for us, it is the same thing for using the natural log as well, because it's the same base, right? So using a log, any log is going to have a common base of 10. Any natural log is going to have a common base of e. So rewriting it into a natural logarithm is going to use the same process. So let's say again, I give you log base 3 of 8 and I want to write it using common bases for the natural logarithm. Well, then I'm just going to say the natural log of 8 divided by the natural log of 3. And when I evaluate that, guess what? I get the same exact value. Pretty cool, huh? So for part B, all it would be is the natural log of 20 divided by the natural log of 2, which approximates to 4.322. Super easy. And really, we don't even need to use this because you guys have your calculators, and in the 5A notes, it gave you the directions of how to put in a different base other than 10. So if you just put in log and a number, that's going to use the base of 10. But if you go to your F4 button and F3 button or whatever it was, the math and stuff like that, that's on your 5A notes, then you can actually put in any other base that you want. You can put in log base 3 of 8 and get an approximation there, and you don't have to use this formula. This was really important for whenever you don't have a calculator, or let me rephrase that, when you don't have a Casio calculator or a fancy TI calculator, maybe you just have a basic 4-function calculator or basic scientific calculator, then you can only press the log base 10 or the natural log base of E buttons, and you can't change the base. So for you guys, it's, you can just use a calculator, but anywho. And then the last problems are talking about those inverse properties. So remember I said at the beginning of this week that logarithms and exponentials are inverses of each other. And so remember throughout this whole entire year, every time we dealt with inverses, let's say we had to solve for an inverse. Well, the first thing we did was switch the x and y and solve for y. But a way to check that two functions were inverses of each other, do you remember how we did that? Yes, no, maybe so. That was using composition. So remember we said that two functions are inverses of each other if f of g of x equals g of f of x, and they're both equal to x. Remember I made you check both of them. I said you got to compose one inside the other, get x, then compose the other inside the original and still get x. If you don't get x for both of them, then they're not inverses of each other. So if we think about logarithmic versus exponential form and using composition, then they both have to equal x. That's the property that I'm giving you in this box right here. So think about log base b of I'll put a for argument is equal to x. So if this is the logarithmic form, then what would be our exponential form. Well, that would be b to the x power equals a, right? So if I put one of those inside of the other, then I'm going to get these two properties. B raised to the x power. That's what I'm getting right here. Well, that would be log base b of x. Other way around. Log base b of some argument. Well, what's my argument? My argument is b raised to the x power. So if I plug in a over here, I'm getting this, which would have to equal x because we know they're inverses of each other. So what does that look like? It says simplify the expression. So notice we have 8 raised to the log base 8 of 4. Well, what do you notice about your number here and your base here? They are the same. The number here and the base here are the same. So what does that mean? That means we're just getting the value of that argument, which would be 4. Okay. Look at part B. It looks exactly like this property right here. What do you notice about the two bases, right? And what do I mean by two bases? Well, you have a base of 7, and then the argument has a base of 7 raised to the negative 3x power. This base and the base of the argument are the same, which means I'm just getting the value of that exponent. So this is just going to be a negative 3x. Looking at part C, what is the base of the exponent? Well, if it's a natural log, it has a base of e. So this base, which is not written in, but we know it's e, and this base are the same, which means I just get the value of the exponent, which is 20. Or the argument of the exponent, excuse me. In part D, we're going to have to do a little bit of work first because my base here and my base here are technically not the same number, but I know that I can write 8 in another way using the same base of 2. Well, how do I do that? 8 is 2 to the third power. Well, that 8 is being raised to the log base 2 of 7. What happens when we raise a power to a power? We multiply the powers. So this is really 3 times log base 2 of 7. Well, looking at our power property, if I'm looking at this exponent of 3 log base 2 of 7, then I know I can rewrite that as log base 2 of 7 to the third power. And now this number and this number are the same, so all I'm left with is 7 cubed, which we know is 243. That one was kind of a tricky one. Okay. Take a look at part E. Our base here and our base here are not the same number, and unfortunately for us, we cannot write 8 in a way that uses 4 as a base. However, I'm noticing something about my exponent, log base 4 of 4. What do you know about when your base and your argument are the same? That's just a value of 1. This is really just 8 to the first power, which is 8. And then our last problem is very similar to part C. We know that our base here is e because it's natural log, so our base and our base here are the same. But I do need to apply my power property to my exponent, so I can rewrite this as e to the ln of 5 cubed. Because this base and this base are the same, it's really just 5 cubed, which is 125. There you go.